Okay. So, in the last class we had these results. Misadjustment M was j by 1 minus j, j was summation of I equal to 0 to n minus 1 mu lambda I by 2 minus mu lambda I. This whole thing is called function ji. So, j is a summation of capital N number of such separate functions. Okay, we have seen M is misadjustment, so it is strictly non-negative. Okay, and when it is stable, it will be finite. So, if we plot M versus J, this is what we had obtained. Other zones we are not interested, because to the right of this point j equal to 1, M becomes negative, and negative M is of no importance to us. Okay. Similarly, if you go to the left, M becomes negative. So, this is the zone, and at j equal to 1, M becomes infinity. So, at least j equal to 1, and if you put j equal to 1, you solve it, numerator will have a polynomial in mu, denominator will have a polynomial in mu. You solve it, if it is equal to 1, numerator equal to denominator, solve it, you get a polynomial in mu, nth order. So, you get n roots at those values of mu, j is 1, and therefore, M does not exist. So, those values of mu are outside the region of convergence, okay, for the algorithm, because if the algorithm, if it converges, that is, if those k prime n, if it goes to finite as n tends to infinity, then only it is stable, algorithm is stable, and if it converges, if it leads to a finite terms, then that summation was, I mean, M will become this, a finite, no other, it cannot take any other value. So, if it is stable, then the misadjustment takes this value only, there is no other value that is possible, all right. So, what we did, we are plotting j. So, j0, j1, j2, we consider the case where lambda is a lambda max. All lambdas are positive because they are corresponding to the eigenvalues of the input autocorrelation matrix, which is positive definite. So, if we consider the lambda max case, see this ji, for any ji, it shoots up to infinity only when your denominator is 0, that is when mu equal to 2 by lambda I at that value. So, if it is lambda max, the 2 by lambda max will come first if we start from origin, and I am not going to explain again. This j versus mu was like this. So, 2 by lambda max will occur first, then again next one, maybe another 2 by lambda max prime, that is next to lambda max the next value, and like this, and j equal to 1. So, these are the values of mu when j equal to 1, that is, if you solve that polynomial thing, okay, you could this j equal to 1 and then solve, factorize the polynomial and get first order factors. You understand what I am saying? If you equate these to 1, then if you have j0, j1, j2, all these kind of things, if you do algebraic addition, denominator will be a product of these factors, so it will be a polynomial in mu. Numerator also will be a polynomial mu, because mu lambda I times 2 minus mu lambda j, 2 minus mu lambda k, like that, and so on and so forth in other cases. So, numerator will be also a polynomial in mu. So, numerator by denominator equal to 1, numerator minus denominator 0, so you have a polynomial equal to 0. So, you factorize the polynomial into first order factors of mu. Those are the values of mu for which equal, it will be, the left hand side will be equal to 0, means j will be equal to 1, and these are those values. Clearly, these are the values at which M will shoot up to infinity. So, these are outside the region of this thing convergence. All right. After that, I did something, but I brought some numbers a, b, c, which are between 0 to 1, and I showed one inequality. I am coming back to that later. But before that, one thing is sure, if M is infinity, that is j equal to 1, those values of mu cannot be part of the region of convergence. That is, these figures k prime I n cannot converge to finite value for those mu, because if it at all converges to finite value, it will converge to this expression where j is not equal to 1, because j equal to 1 means infinity, so it will not converge. Converge means converging to a finite value. But we have seen if it converges, it will converge only to those, okay, this figure with j not equal to 1, so that it is a finite value. Therefore, those mu for which j equal to 1, they will be outside the region of convergence. So, these are the mu's. Let me use some other ink. So, this is one mu, this is one mu, these are the points which lie outside. Now, what happens to the intermediate regions between two red dots? If I take that mu, does this converge to finite value or not? That I do not know. But if it converges to finite value, it will be finite. Okay, it will be finite, you will take this expression. Alright, this much. So, I know that at these points, this function shoots up to infinity. So, k prime I n does not converge. Okay, it has to not only converge to m, it has to converge to a finite m. So, those are the values where this will not converge. But the intermediate range and all I do not know. That is because, as I told you the other day, let me go to a new page. If you take an expression like, say, suppose 1 plus x squared dot dot dot, it gives rise to a function f x equal to 1 by 1 minus x. For this, mod x should be less than 1. Okay. So, x equal to 1. So, this zone 0 to 1. Okay. Suppose x is positive, real and positive, to make life simple. So, 0 to 1. For that region, this summation converges to a finite value, and if it converges, it will take this value. But when you look at this function, forget about the series, this function does not exist at x equal to 1. So, x equal to 1 cannot be a point of convergence here, because if it is a point of convergence, it will converge to this value with a finite value for this. This function is a finite value. At x equal to 1, that does not happen. So, x equal to 1 cannot be a point of convergence, because point of convergence means this summation will converge to this function with a finite value. That is not happening here. So, x equal to 1 is ruled out, but x less than 1 greater than 0, I am assuming x to be, say, positive, otherwise you have to go from minus 1 to 1 if you want to be precise, mod x to be less than 1. So, any of these values here, take any of the value, this will converge. But when you look at the function, function does not exist at x equal to 1, but it exists at x greater than 1 also, at x less than 1 also. Only thing is at x equal to 1, function does not exist, means that is not part of the region of convergence of this. So, this much from the looking at the function, this much we can say that that point where it does not exist, the x equal to 1, that cannot be region of convergence. But the function I know, giving the function, it exists for the x greater than 1 also, less than 1 also. Okay. In fact, it is better if I put it just x greater than 1. All right, only it exists. Only x equal to 1 does not exist. So, from the function, by looking at the function, I can make out that it will not converge here, okay, or here. But the function exists on this side also, function exists on this side, function exists in this intermediate region also. Okay. Of all these places, some zone may be a region of convergence for this series. Now, I see one thing, if I put x equal to 0 in this series, it is 1. So, it is a finite value. So, x equal to 0 is okay, it is a region of part of the region of convergence. And 0 to 1, then what will happen if it converges at a value of x equal to 0, and then I increase x by very small amount, epsilon, very small amount. okay, it will still be, it will not suddenly shoot up to infinity because epsilon is very small. So, there is a neighborhood and it will go on like that till we find a point where the summation will finally shoot up to infinity. Its value will be increasing. When you give x equal to 0, its value is 1. If you give x equal to epsilon, maybe some positive number, value will increase, still increase. But finally, at x certain value, this function will this will be shooting up to infinity. So, it will not take this function with a finite value. That happens at x equal to 1. Before that, so it will continue to be like this, okay, going up. So, any this from 0 till we reach here, we do not touch this, but in this point, this range converges. Okay. So, we find out one point of convergence at x equal to 0, and from that we go to the point of discontinuity, point of not divergence, not convergence. Till that point, don't touching the point, this will converge. Okay, this will converge to this form. This is the thing we bring here. We know that the LMS algorithm Wn plus 1 Wn plus mu xn En. So, W1, if you take n equal to 0, n equal to 0, W1 is W0, and suppose I take mu equal to 0, then this is 0, then W2 will be W1, which is again W0. So and so, because mu is 0 means no update, so initial value W0 continues at W1, W2, W3. So, error was that component Vn. Okay. Vn is, we know Wn minus W opt, but Wn, whether Wn is 1, n is 2, n is 3, is constant, which is W0. So, Vn also constant, initial value minus W opt. So, any component of n, Vin, will be Win Win minus W opt I is constant, because Win is constant. W1 is same as W0 if mu is 0, W2 is same as W1 if mu is 0, and W1 is W0, so on and so forth. So, all the filter weights remains constant at W0, okay, in this case, mu equal to 0 case. If mu equal to 0, then what happens to that error vector, weight error vector with respect to the optimal weight? So, W at nth point of time we know it is Wn minus W opt, but Wn does not change. It is same as W0, W1, W2, W3 are all same. So, that is why Vn also constant. If I take any ith component of this vector, say Vin, it will be ith component of the filter weight vector minus ith component of this, and that is a constant because it is not changing with time. So, if that be, then variance of this does not change, it is finite. Okay. That means Kin less than infinity for all n, because variance does not change, it is just a constant difference, Win minus W opt I, and Win is nothing but Wi0, because at 0th point of time, that initial value whatever I gave Wi0, that remains the case for all n. So, Wi0 minus W opt I, it is just finite number, it does not change as n changes. So, as a result, variance also does not change, is a constant, variance is just the square of it. Okay. That also remains finite for all n, and if it is for Kiin, same for this is just a transform version of that, all right, which means mu equal to 0, this always remains finite. That means mu equal to 0, this is a point of convergence. And not only that, we have already seen if mu is much less than 1 by tracer then it is, algorithm is stable, m remains finite and all that we have seen earlier. Alright. In fact, you can say mu is much less than 2 by tracer also, that will fine. But 2 by tracer, because 2 by lambda max, we know lambda max is less than, sorry, it is less than summation of all the eigenvalues, right? All eigenvalues are positive, one of them is lambda max, others also positive, so summation, and that is trace. So lambda max less than trace by r, less than tracer. So 2 by lambda max is greater than 2 by tracer. So 2 by lambda max, 2 by tracer will be somewhere here. So if mu is less than this, we have seen already m is finite. So that means from mu equal to 0, if you go further to the right, we are still in the region of convergence, and this will remain so till we hit this point, first point where j turns out to be 1, and therefore m shoots up to infinity. So at least this much we can take to be our region of convergence. There may be other, these places also possible. Maybe mu, if I take from this region or some other region, maybe it is possible that m also will remain finite for them, but I am not sure. But about this I am sure, because mu equal to 0 is a point of stability up to, in fact, as long as mu remains much less than 2 by tracer, they are all points of stability, and therefore I can go up to, I can increase till the point time I hit this point where m shoots up to infinity, because j touches 1. All right. So I will be just finding out this range. That means I will find out at what point this will become 1. Let me draw again. See, these are the points. These are the points. Okay, let me draw again. This is my j, this is my mu, and j will shoot up to infinity at 2 by lambda max, then next time 2 by lambda max prime maybe, like that. So it will be like this. Next one, again next one. It will be like this. J equal to 1 is the k-set point. So this is this fellow, this fellow. These are the points of discontinuity. But I have seen at least one thing: if I remain to the left from 0 to this till I hit this point, because this mu equal to 0 is a point of stability, and then if I go further to the right, at least as long as mu remains much less than 2 by tracer, m, this is stable because m remains finite, and if I go further and further, this increases till we hit this point. So this will be at least a guaranteed region of convergence in mu. There may be other places also. Okay, there may be other places also, like from here if I go up to the next point, maybe here also it is fine. If I take mu from here, m will be finite, but I am not sure. I cannot work that out. That is very difficult maths, very tedious, but I can work for this part. That at this mu from here to here, if I take mu from here to here, I will be within the region of stability, because mu equal to 0 is a point of stability. Then as you go along till 2 by tracer is stability, and you can extend further till it becomes mu equal to this point, for which j is 1. All right. That means you have to equate that j equal to 1 and find it out what are the values of mu for which j equal to 1. Take the one which is smallest, but that is again very tedious. Okay. That is why we will not be using this. I will do some further, I won't say approximation, I will apply further tricks. We have seen already that if A, B, C they are between 1 to 0, so that A plus B plus C also between 1 to 0, which means A plus, they are positive, so that means A plus B is between 1 to 0, B plus C between 1 to 0, A plus C between 1 to 0. Then A by 1 minus A plus B by 1 minus B plus C by 1 minus C is also less than A plus B plus C by 1 minus A plus B plus C. If you can generalize, suppose A1, A2 dot 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 AN, maybe A0, A1, sorry, there are some constants between 0 to 1. So that A0 plus A1 plus dot 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 AN minus 1 is between these. Then we can extend this A0 by 1 minus A0, A1 by 1 minus A1 plus dot 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 AN minus 1 by 1 minus. This is less than summation of these terms A plus B plus C. Now it is summation AI by 1 minus the same summation, right. Now, why I am doing this, consider the expression of J. Ji is mu lambda I by 2 minus mu lambda I. So, you take 2 common, it is half mu lambda I by 1 minus, right. So, we have got this for J0, then right. We have seen mu should be less than 2 by trace R. This comes from the convergence in mean condition, right. That means what is tracer? Summation of the eigenvalues. So, mu into tracer should be less than 2 or half, that means half, if you take 2 here 1 by 2, half mu into trace R. Tracer means lambda 0 plus lambda 1 should be less than 1 and of course greater than 0. If mu is greater than 0, trace is greater than 0. But what does it mean? Half mu lambda 0 plus half mu lambda 1, half mu lambda 0, half mu lambda 1. Their summation less than 1. Okay, and they are individually also they are between 1 to 0. Okay, because when you take all the eigenvalues, then half mu and summation of the eigenvalue it is less than 1. If you take only one eigenvalue and all are positive, then obviously half mu lambda 0 less than 1, half mu lambda 1 less than 1, half mu lambda 2 less than 1, and like that. So, these two, okay, maybe I can take one more term here. If I take these two terms, if we call this A, numerator A by 1 minus A plus B by 1 minus B, A is definitely between 1 to 0, A is half mu lambda 0, because with half mu and all the eigenvalues summed and all are positive eigenvalues, if that is less than 1, so if you have only one eigenvalue or two eigenvalue multiplied by mu and half, that is obviously between 1 to 0. So, this is between 1 to 0, if you call it A by 1 minus A and B by 1 minus B. So, this part will be less than A plus B by 1 minus A plus B. Then again A plus B means half mu within bracket lambda 0 plus lambda 1. Again, if you take half mu, just lambda 0 plus lambda 1 only, remove other eigenvalues. Obviously, it will still be less than 1 greater than 0, because with all eigenvalues which are positive added, it is still less than 1. So, if you take just two of them, obviously it will be less than 1. So, half mu bracket lambda 0 plus lambda 1, if you call it D, So, d by 1 minus d, d is also between 1 to 0, okay, and next guy d is also between 1 to 0, and their summation half mu lambda 0 plus lambda 1 plus lambda 2, that is also between 1 to 0. So, that will be, this will be less than d plus, if you call it c, d plus c by 1 minus d plus c, and go on doing it. So, it will be finally that is half mu trace of R, because summation of eigenvalue is same as trace of the autocorrelation matrix. That is what I have used here. Okay. So, let me call it a function of mu. So, this function is above j. For any value of mu, j is less than f of mu. That means, if I plot f of mu, it will only, at any value of mu, it will be above this. So, it might be like this, f of mu, because at any point of mu, f of mu will be above this, which means it will cut this a equal to 1 line earlier here, before this point, and that is within the region of stability, this much. That is to the left of this point of instability or divergence, there is non-convergence, this point is to the left of this. So, now what I will do, I will take only this segment as my region of stability. I know some points to the right will be missing, but I cannot find them, at least this much. If I take, I am guaranteed that m will not shoot up to infinity, and therefore, algorithm will be stable, then excess mean square error variance will not go up, all that. So, what is this point? This point is when f mu, this curve equal to 1, and f mu was, what was f mu? Half mu trace R by half mu trace R. If that is equal to 1, so you take to the, then this will basically mu equal to 1 by trace R. So, this point is all right, 1 by trace R. So, for convergence, for stability, we need mu less than 1 by trace R. This zone. All right. If you choose mu here, your algorithm will be stable, m will be under control. Okay, will be finite value. So, the excess mean square error variance will not shoot up to infinity. So, I stop here today. We have done enough analysis of the LMS algorithm, both first order and second order. There is convergence in mean, and that weight error correlation matrix or covariance matrix, a variance of that, whether it shoots up to infinity or not, output mean square error, epsilon square mean, or that rather excess mean square error normalized, which is misadjustment in the steady state, whether that remains finite or not, all these things we have analyzed. I did not give proof of some of the results, because that is beyond us now, given the paucity of time. But with this you can work out, this is your region of stability. All right. So, this much for today, and I will join you next time. Thank you very much.